So last week there should have been two activities. Yi came along, I think, on Tuesday and introduced you to COMSOL on Hammer, and so I think he went through how to do that. Hopefully you've also gone through the material we have online for the stuff on triangle elements. I'm trying to think exactly what we went through. But just to recap, so far we're talking about flow problems only. We chose to do that, as you know, because there's a single degree of freedom or a single dependent variable prescribed at the nodes. The variables at the nodes are defined as either heads or fluxes. Fluxes are not vectoral quantities, they're just scalar magnitudes which are positive or minus, negative, depending on whether they're in or out. For steady flow problems and for transient flow problems, we've derived a governing equation which looks somewhat like this, which you'll have seen. And in putting this together, what this allows us to do is to define the conductance matrix as a function of a constitutive relationship, which is Darcy's law, written in our case in terms of heads and flow rates, velocities of flow, and a matrix which is dependent on the dimensionality of the problem, 1, 2, or 3 dimensions. It's dependent on the kind of element that we have, whether it's a two-noded brick element or a three-noded triangular element, which we talked about last time in online, and varies also in terms of the number of degrees of freedom we have. So we'd have a different form of this A matrix if we're solving a problem that is either heat flow, fluid flow, or mass transport, Fickian mass transport, because all of those have as their variables scalar variables, which have just 1 degree of freedom per node, versus whether we're looking at mechanical problems, say in 2 dimensions, where you could imagine that we have displacements in the x and y direction. And so that's the basis of what this is. So I presumed you looked at this and went through it. The basic idea, I think, I could play it to you, but I'm not going to. I'm just checking exactly what was on there. This may be completely incoherent. But the basic idea is that although this analysis isn't couched in terms of shape functions, implicitly we do use shape functions which allow us to link nodal values of head at 3 of the nodes, nodes I, J, and M, which are on this triangular element, and a weighting function which allows us to define the head at any particular point where we want to write it. And so these are the shape functions that we kind of defined when we talked about the Galerkin method. And these are the same shape functions that we will develop when we look today at isoparametric methods. And so if you went through this, you'd have seen that we again localize it by defining a conductance matrix for an individual element. If we can write that conductance matrix for a particular element, then we can index the nodes in terms of the global node numbers, 1, 2, and 3 in this particular case, relative to local numbers, which are these numbers here. And in doing that, it allows us to be able to put together a global system of equations. And so it's starting to get repetitive because we've done it before. And the skill in this actually comes to just defining the individual terms which are part of this A matrix, which is just a 2x3 matrix. And there are a couple of examples which, first of all, cemented, hopefully, the magnitude of the conductance matrix, and noted a couple of things about that conductance matrix. And those were that, one, it's symmetric, it's positive definite. And so if you look at the components above or below the leading diagonal, they are symmetrically disposed about that. It's positive definite in that all the terms on the leading diagonal are non-zero and positive. Positive and definite is means that they're not positive values, and definite just means non-zero. And the other interesting component, I'm not sure whether it's pointed out, is that all of the rows sum up to, in this particular case, sum up to 0. And they sum up to 0 because if you, for instance, put values of head on a single element of unity on each of the nodes, then by definition the gradient on that element is 0, and therefore the net flux into or out of that element has to be 0 also at all nodes. And the only way that that can happen is if the values of these, the rows are all summed to 0, and solves a particular problem just for a very simple problem for Darcy's law. And so that's where we left it. So now I know exactly what you looked at. The plan is today to be able to take this the next step and to do this and talk about fluid flow and pressure diffusion, again for not for two-dimensional elements, but actually for 1D elements, I guess. Seems like I'm using a blunt instrument. It's better. Okay. So what we'll talk about is we're going to talk about what we refer to as isoparametric elements. And we're switching back not to apply those to these triangular elements that we dealt with before, because that's a little more complicated than we need, but we will look at specifically behavior for a one-dimensional case. And so implicit in this is what isoparametrics are and how they work. And again, we'll derive this for a 1D case on our direction to be able to define behavior for the 2D cases or the 3D cases. If you look at a code like COMSOL, all of the elements that they use for triangulars or quadrilateral elements are all isoparametric elements, kind of the industry standard. And so it's not really that far removed from the stuff we've already talked about, but it's a slight evolution. And the idea is basically this. So if you were interested in solving a problem, say for a well, and we're looking at flow into a well, and if we draw this in perspective so that this was the well that flow is occurring into, then one way that we could do this is to take a two-dimensional geometry, but realizing that as you go around the well, the geometry that you see actually repeats itself, then we actually don't need to make a three-dimensional geometry that includes this well. We could actually get away by really just drawing basically a wedge of the cake. And the wedge of the cake would be what we'd refer to as axisymmetric elements. In other words, they repeat themselves as you go around. And so you only need a two-dimensional geometry to be able to represent the behavior as you go away from the well. And because of the observation that as we flow from the exterior, what are we doing here? Into the interior, that we have a flow rate that has to be maintained, then by continuity, the volumetric flow rate as you go closer and closer towards the well, and the thickness of the flow domain shrinks, then the flow rate has to remain itself constant. And so since by Darcy's law, Q equals the cross-sectional area times hydraulic conductivity times the change in head with radius, this area here changes as you get relatively small here and relatively large here. And so since the only thing that's changing other than the area can be the gradient, then by definition the gradient has to get sharper, steeper as it gets closer. So you'd expect the gradient to look something like this as you went progressively further away from the wellbore. And so these relatively steep gradients are something that you might want to be able to pick up by having more elements there. And so using the idea that we had for triangular elements, you could actually mesh this so that as you get further away from the well, you have fewer elements present. and you get progressively closer and closer, you have progressively more elements present to be able to allow you to have more nodes. Because when you solve this, as you go from the wellbore to further away from this, this would actually give you 1, 2, 3, 4 nodes, and they would be spaced non-uniformly. First close in, so you can capture this gradient, and then further out as you go here. So the idea is that you could do this in a conventional way by taking the triangle elements that we talked about last week and using those. Or alternatively, what you could do is you could take elements where you have the same element coverage. So here's an element here, and here's an element here. They're exactly the same size. But in addition to these elements, we've made them so that we've added some extra degrees of freedom or extra nodes on the mid sides. We could actually add them extra nodes here as well. And so they're more complicated elements. And so what we've done is we've used the same distribution of elements, but we've increased the density of nodes by just choosing how to put those closer to the area, which would be in a high gradient. And so these so-called isoparametric elements are these elements where we choose exactly where we put the nodes. And so isoparametric elements, I guess, refer to two things. Parametric means that the shape functions that describe the variation of head as we go across this system, which is really what the shape functions do, could also be used to be able to describe the geometry of the element. And so although we've drawn these elements here as being prismatic with straight sides, there's no reason why we couldn't, if we wanted to have a curved boundary, actually have one of these straight sides be slightly curved. And if we wanted to do that, then what we could do is we could use the same shape functions to map the parameters on the element as we do the geometry. And so ISO really refers to the fact that we use the same function to map both the geometry and the dependent variable across the system. And we can also define other cases as subparametric elements, where we use a lower order shape function. So in other words, if you wanted to have a shape function that defined behavior along an edge and it's straight, then you can define that in terms of a straight line between 2 points. You don't have to know the location of this intermediate point. But if it's curved, the only way that you can represent this geometry is by using a quadratic, something with a squared term in it, instead of just a linear term. And so subparametric and superparametric are cases where you use a shape function that is lower to map the parameters on the system than it is to map the geometry. And superparametric is where you use a higher order shape function to map the parameters on the system than you do the geometry. So it's, I'm not sure we have to belabor that point. But the idea of isoparametric mapping or parametric mapping is merely this. You know that when we calculate the conductance matrix, that we have an integral which is defined in terms of these parameters. This is our constitutive equation that we've set. So d is equal to, what is it? V is equal to d times, we've used a shorthand of dh dx, and this is a velocity. So this is the conductance matrix, basically, or Darcy's law. And the A matrix is what? It's something that links gradients of head to this and nodal values of head. So these are the basic forms of these two matrices that we need to be able to populate this particular relationship here. If I do this, A transpose is the same as is the transposed version of A. And so these inhabit an integral. And so it just happens to have been fortunate in the cases that we've looked at so far, both for the prismatic system and also for the triangular element, that one, we take the element to have a single value of hydraulic conductivity. And so if that's the case, then this certainly doesn't vary as you go from x or y in the direction within this element. So this is constant. So D is constant by definition. So that's helpful. Also, in the cases that we've looked at before, both in the prismatic element where you have a nodal value at node 1 and node 2, the variation in the heads between those has been linear, and therefore the derivative of those is constant. And so both for the triangular element that we've dealt with and for the linear brick elements that we've dealt with, the value of A has been constant as well. And so the net result of that is that we can take this integral and we can write it like this, in which case we don't have to deal with it. And so these are all constant, they come outside the integral, and therefore we don't have to do it. We can just calculate what the integral is, which is just the area of the triangle times its thickness, or the area of the prism times its thickness as well. That's all this integral says. In cases where we use more complicated representations, one of the geometry, so this isn't just a prism anymore, but it has actually a kind of complicated shape in x and y. So the limits of this integral now are no longer really quite well defined. It's not between a portion which is just defined between, right? This would just be integrated between x1 and x2, and this would be integrated between y1 and y2. So instead of that, we have this complicated geometry which we have to deal with. And the second is that if we use shape functions which map the variables, say with mid-side nodes, then by definition, as we've already alluded to, the shape functions can't just be linear shape functions where when you take the derivative of them, a term which is linear, a times x, if you differentiate a times x, it just becomes a. It becomes constant in here. So we're left with portions that actually vary within the bounds of the element. So for two reasons. One is because the limits are no longer simple, as we would like in this case. And secondly, the magnitudes of the A matrix probably aren't constant with location. So if you calculate what the A matrix is at this point for any term, and you calculate what it is at this point, they won't be the same. And so that's the reason that we want to perform this, use these isoparametric elements. So the basic idea is this. So we take the existing element, we map it so that it looks, instead of looking like this, it actually maps it onto a bi-unit square. So it's 2 by 2 in dimension. It happens to be centered on 0, 0 in terms of local coordinates. And if we do that, then we can very straightforwardly evaluate this integral, because all of a sudden now the limits are quite easily defined, as they would be here, because now it's mapped, as opposed to here where they actually vary along this line. And the second is that if these components happen to vary with location, we can do that merely by accommodating the fact that we can calculate the magnitude here, we can calculate it here, we can calculate it here, and we can calculate it here, and we can use those values to be able to numerically evaluate this integral. Come on in! So I can see a silhouette at the door. And so that's one part of it. And the other part is that they have this interesting component here, which is a determinant of a Jacobian. A Jacobian is just a fancy name for a matrix of partial derivatives. And it's just a way of being able to map geometries from one scale to the other, which we'll see as well. So in other words, if you have a component here which is something, has a side length on it, which is dx by dy, if you can see that, then you'd expect this to exist here. It wouldn't be the same geometry, but it would have a component which has a size which is dr and ds. And so in mapping this little patch, differential patch from this location onto this location, and you'll see that this term here goes from here to this, is that we can apply some scaling parameter. So that if going from this size here to this size here, we have to stretch it or squeeze it in different directions, then this parameter here exactly takes care of that change in dimension. So, to not lose sight of the big picture though, the idea is this. You have a complicated geometry that you want to figure out. You map it onto very simple geometry. You calculate what your K-matrix is, and then you remap it, but actually don't remap it. The matrix is the matrix, and it represents this true behavior that you want to deal with. And so that's the idea of isoparametric mapping. And what it does, it allows you to be able to do two things. It allows you to use shape functions which are much more complicated and can represent, say, things like mid-side nodes and central nodes within the element, and also shape functions that will allow you to represent curved sides on things. And so those are the two things that we'd like to be able to do. The real meaning of isoparametric refers to the fact that iso being one, meaning one-to-one, one and one only if you like, is that if this was your geometry, that is your real geometry of the element that you have, that you like to be able to represent by figuring out what the K-matrix is, the conductance matrix is, then when you map it to this form where you're going to do the calculation, the mapping should give you that every single point on here would be a unique point on this mapped form. And if it's folded in some way by the shape functions, then clearly in this case, the point that's here would also represent this point here. There's 2 points that are on this that are mapped onto each other. And that would suggest that the shape functions that you're using to doing this mapping are no longer inadmissible because 2 points in this geometry are ending up at a single point in this. And so it has to be that every single point on this populates a unique point on the map geometry. And so you'd have to unfold this. And so this is just saying that the shape functions that you choose to represent that would not be admissible. Okay. So in the integration that we're talking about doing, so we suggested that we would like to be able to do this integration of A transpose dA. And in this case, it'll be in the x and the y directions. Then what we'd like to do when we map it is that this integration merely becomes one which, instead of being over the area of our system, is actually just defined same matrices as before. But now what we're going to do with this is that you can take on trust for now the fact that we'll take a scalar value. This is just a single number for our intents and purposes, which is multiplying through by this coordinate system, which is revised. Instead of being x and y, it's now r and s. And so the idea of this is that this is now between -1 and +1. Again, -1 and +1. And it really is that the mapping that we're attempting to do by this transformation is merely that we are scaling it in some way so that these two terms are equivalent to each other. And the equivalence, if you like, in this way, if you wanted to, I suppose if you wanted to, you could also write this in a slightly different way as being this multiplier is just equal to, and we can write it, I'll write it, x in this case is r, and dy ds. I'm just rearranging that previous equation. And so if you look at these individual terms, dx over dr is just however big this length was here in this image to however big it is in this image. And the ratio of those two lengths is this number. And likewise, the length of the same patch in each of these cases, in each direction, both the global system and the local system here is this here. And if we know what those numbers are, then we get a scaling value that just maps one to the other. So it allows us to map from one system to another, nothing more than that. And so if we had a one-dimensional element, which is the one that we'll deal with first, the geometry is just this. We only have x in this case, so we've lost y and s. So we have a global geometry which looks like this, which has a length L. We have a local geometry which has a length which is equal to 2. And if the mapping is piecemeal uniform, so in other words, if we take this geometry and we squeeze it uniformly to get it into this second geometry here, so that every single portion of this gets reduced by the same amount as you go along here, just uniformly squeezed, then we can straightforwardly write this as just dx is equal to the determinant of the Jacobian, dr. And so in this particular case, the determinant of the Jacobian, just by rearranging these terms, is dx over dr. And if we take the actual size of this, then over the whole length of this is L. And the bi-unit square, I guess the bi-unit length, is 2. And therefore the magnitude of this mapping function to move one to the other is just L over 2. Nothing more than that. And so that's basically the idea. So what we'd like to do is be able to do this mapping. And to do that, we just have to have some way of being able to change the sizes of the two elements and map between them, and be able to write the matrix in terms of these local coordinates. And go ahead with that. So to do that, then, let's look at this. This is the idea. So we start off with this geometry. So this is our global system that we've defined before. It has some length to it between nodes 1 and 2. The length of it is L. At each of these nodes we have a magnitude of the head defined. I guess it would also have a magnitude of the flux defined as well, one of those two values. Likewise at node 1, be Q1 also. It has a coordinate. It doesn't really have a y coordinate because it's only really the length of the individual elements that we're interested in. So it really only has an x coordinate along the length of it. And it has some parameters that define its hydraulic conductivity and its cross-sectional area, because we're going to just have doesn't actually have to be a uniform area. It could be a varying area as you went along the length of it if we so wanted, but we'll choose a constant area in this case. At the local level, we have this bi-unit line. So the origin is at 0, 0. It has node number 2, which is corresponding to this. So if you like, this is the node that maps onto this. These just map onto each other. So it's uniformly taking this larger element of the global sense and it's squeezing it down to get it to the local case. Again, it has these nodal values of head and flux at node 1 and node 2, but it just happens to be over a different length. And so if that's the case, then our conductance matrix is just going to be equal to, I suppose we could write it as integral A transpose d A dx dy dz. If the area is constant, then we can write this as an area times the integral A transpose dA dx. And this is the component that we want to be able to map from a length here, which is dx. Don't know if I can draw that. This has to get narrower as we go down, I suppose, right? Taper down. Haven't done a very good job of that, but you can hopefully imagine what I'm trying to do. That's not what I wanted. And this length in here, can you see that, by the way, or is that too small? Okay, this is dr. And so this now just becomes area integral A transpose dA, this scaling parameter, take it on trust, and dr. Well, actually, I mean, we've already said exactly what this is here, that this is, so what we could do is we could just write this, multiply this by dr over dr, right? And if that's the case, then if we combine these two together, then by definition, this term here is just equal to this term that scales between these two geometries, dx dr. Nothing more than that. So in other words, you take our original relationship here, you multiply by 1, you arrange that 1 so that these terms are written together and this is left out, and this term here that's circled becomes the determinant of the Jacobian. So the Jacobian is J, which is, a Jacobian is just a matrix. In this case, it's one term, a matrix of partial derivatives. And the determinant of it is just combined in some way to get the average value of the stretching as you go across it. Okay? So that, I think, brings us down. I'm going to go back to this because I like red for some reason. So that brings us here. It's a bit fuzzy, but you get the picture. The limits now, instead of being between 0 and L, this would be between 0 and L, are now between -1 and +1, which is this, and the rest of this is here. So in the same way as before, we want to know exactly what the individual components are. We need to know exactly what this matrix is in terms of the local coordinates, and we need to know what this matrix is as well, and everything else we can get. The conductance matrix, Darcy's law doesn't change, so this would just be a single value. This is hydraulic conductivity, K, not to be confused with a matrix equation. So this is hydraulic conductivity in Darcy's law. I guess this is this. And then the other thing that we need to do is we need to do something about the mapping of this. You remember that before, that what did we do? We provided shape functions. And then we kind of call them shape functions. But they're slightly different from the ones that we'll use here. So the shape function we used before said that we could calculate the head at any point, and it's equal to, let me figure this out, 1 minus x over L times h1 plus x over L times h2. So that the head was equal to this term here, B1, multiplied by, well, sorry, not multiplied by, This is just writing the equation above as a matrix equation. Right. So B1 is this term here. So this is B1 is this term here. And B2 hopefully is this term here. And you can prove to yourself that this is right, because if you want to know what the head is at this particular point here, this is H1. So if you put x equal to 0 in this, then this term becomes 1 times H1 plus 0 times H2, and so it gives you H is equal to H1 at this point. Conversely, if you take this point here and you put x is equal to L, then x is equal to L gives you nothing here, and x equals L gives you 1 here. So at this point, the head would actually be H2, so you recover those values. So these are valid magnitudes of these shape functions that allow us to map the heads as you go across this element. If we wanted to, we could also substitute values for the coordinates in this, x1 and x2. So if you wanted to calculate what the x-coordinate was at each of these locations, then you can use exactly the same rationale, because this would now give you x is equal to x1 at this particular point, and x is equal to x2 at this particular point. And so we used that when we talked about these one-dimensional elements. But these are our shape functions that we didn't really need to define as B1 and B2 because we used them as is. So now what's different is that instead of writing our shape functions in this geometry here, what we're going to do is we're going to write them in this geometry. And we can write them slightly differently, and we're going to choose them to look like this. So if the shape function matrix that we have, I go back to red again because it's just more legible. So this is B, if you can't see it, this is B underlined. So it looks a bit like this. It has these two components, B1 and B2. So this is B1, and this is B2. And they're called serendipity shape functions just because they're chosen by chance. And the requirements that they have to meet is that they are equal to 1 at the node in question, and they're equal to 0 at all other nodes. And so if we drew these things out, and I'm going to draw these things out, I'm just going to find a piece to be able to draw this, is that if you take our one-dimensional element, which looks like this, instead of being drawn from in the x direction, it's drawn in the r direction. This is r. This is node 1, and this is node 2. I guess I should also make this the fact that this is the intermediate point, right? So this is 0. So this is 0. This is r equals plus 1. And this is r is equal to minus 1. And if we draw what those shape functions look like, then they look like this. They're going to be, that's not bad, that's 0, right? So this height here is equal to 1. This height here is equal to 0. And this is going to be B1. And the other shape function is going to exist here. You have no idea how difficult it is to write with this thing. Well, you probably can't imagine because you're looking at it. And this is B2. And so if you look at the equations of these, so B1 was equal to what? It was equal to a half 1 minus r. Is that right? Let me go back. Yeah, half 1 minus r. So this is a half 1 minus r. And this is equal to a half 1 plus r. That's just the equations of these. So this is minus 1. So these should actually cross each other right at this point, right? So these, the red, blue, and green, if you can see those colors, should all go through the same point. And it should be equal to, so I guess this height here should be half, I think, right? Just by this expression. And these are just the equations of these lines. So in other words, at r is equal to minus 1, then 1 minus minus 1 is 2, divided by 2 gives you 1. At this point here, r is equal to plus 1, so 1 minus r is 0, so this point is 0. At this point here, this is r is equal to 0, so 1 minus 0 times a half is just equal to a half. And so physically what these mapping functions are that they map things between those. So the other behavior, I guess, that you can see here that's apparent is if you take a section here and you drill down through here, and if you look at this height of this line here and add it on here, it would give you a line that gives you a straight line across the top. In other words, if you add the blue and the green triangles together, sum them up, then they just equal unity everywhere. And so these are the shape functions. We mentioned that they satisfy two requirements. They equal unity at the node in point in question. So B1 is equal to unity at node 1, but it's equal to 0 at all other nodes. B2 is equal to 1 at node 2, but it's equal to 0 at all other nodes. There only is one other node. And so these shape functions that satisfy that, when you combine them together, then it just gives you, for instance, h is equal to b1 h1 plus b2 h2, which is the same as saying the vector of shape functions multiplied by the nodal heads. Or you could also write it that the x-coordinate anywhere in the element is equal to b1 times the x-coordinate of node 1 plus b2 times the x-coordinate of node 2, which is b times x. And so this refers to the fact that we can use exactly the same shape functions to be able to map the geometry and the dependent variables across the element. So that's maybe more than we needed to do. So let's go back to this. So we have exactly that here. And so this is where we are. 1 minus r, 1 plus r. We can map the geometry using those shape functions. We can map the head using those shape functions. And so our reason to do that is because we know that these individual matrices that we need those derivatives. So this A matrix is what? We know that H is equal to so this, by definition, if we write the values of this is just the derivatives of those shape functions. Likewise, if we want to be able to, for instance, define the value of this, what did we say that the value of this has to be? This has to be dx over dr. And so if we know what the nodal behavior is because of this, then we can merely take the derivative of this with respect to r to be able to figure out exactly what this Jacobian is. So we're going to use those individually to figure out exactly what's going on. So let's do that. That's kind of the bottom. So I've spent a bit of time making this point that they have to be 1 at the node in question and 0 at all other nodes. In our case, they happen to be linear because we only have two nodes rather. And so we can figure out what each of these terms are. The A matrix first. So there's two things we're going to have to figure out. We want to know what the A matrix looks like because we've got to put that into this expression, and we want to know what this Jacobian is. Everything else we know. We know the conductance term, that's just Darcy's law. And the only other two terms are these. So let's take each of these one in sequence. First the A matrix, and then the determinant of the Jacobian. So by definition, the A matrix is this. It's something that takes the values of the nodal heads, nodes 1 and 2, and converts it into a gradient over the element. So what we could do is, in this simple one-dimensional case, we could just write this out as dh dx, and what could we do? We could multiply both sides of this by dr over dr. So this is 1. And dr over dr are just these terms here. So we could take this derivative and we could just manipulate in some way to get that. This all of a sudden becomes a composite term which includes two parts. So one is a change in head with r, and one is the geometric component. And so what we could do is we could first of all take this first term, which is this, and we note that the head is equal to what? Head at any location is equal to the shape function multiplied by the nodal values of heads, right? Nothing different from this. This is this expression here, and this is the same as this expression here, right? Depending on how you like to think about this. And so what we can do is we can, if we want to know what this second term, first, I guess, call this term 1. Term 1 is we can substitute into this for the heads at any particular location being a function of nodal values, which only exist at the nodes, and shape functions, which are just values which map it. And if we do that, this is this expression here for this. And if we realize that these are constant, then we can take those outside the differential. Right? They're just values h1 and h2. They exist at the nodes only, they don't exist outside those nodes. And so the only derivative that we have is this. And so a simple way of writing this is b prime is just the derivative. And of course, what's the derivative of the shape function? If I can do it. What's the derivative of 1 minus r with respect to r? It's just going to be equal to minus 1, because you lose this term. And 1 plus r with respect to r is just plus 1. So if we take the derivatives of this term, then we end up with these slightly different values. And that's exactly what you have here. So this is our relationship b prime. And so in other words, that's our derivative with respect to r. And so that's the first of these terms that we have. The second term that we have is this, Roman numeral 2. And so I'll draw a line across here. And so Roman numeral 2 is down here. And, well, what's that? So we want to get the derivative of r with respect to x. It's not so easy to do that, but what we could do is we could get derivative of r with respect to x is equal to 1 over the derivative of x with respect to r. Just reciprocal, right? Just writing it upside down. Whoops, sorry. And so if we believe this, that we can do this, so this is what we want, we can write it like this, which is this. And the reason we write this is because we know that if we substitute in that the x-coordinate is equal to the shape function multiplied by the x-coordinates of the nodes, which is this, then well, it's basically this here. And we know what the shape function is. We know what the shape function is, we know what the nodes are in terms of their coordinates, and we could substitute those. And so we, in matrix form, we can write the expression like this. And if that's the case, then we know that we can get this. So, right, this is just the derivatives of the shape function. Remember that b prime is equal to, is it minus 1? Yeah, minus 1, equal to minus 1 plus 1 times a half. We did it up here. And this is just the magnitude of the x-coordinates. So we have that. And so this is our second term that we've got. And so if we refresh our memories of what we were trying to do was we need to get the value for this matrix because it defines the A matrix. We can do it but just by multiplying by 1, and if we do that we end up with two parts. One which is the change in the nodal values mapped over the element in local coordinates, and the other one is this term which relates the length of the local element to the global element. It's just the differences in the lengths really. But what we can do is we can, as a function of our shape functions, we can define this term here as this. We can define this term here as this. And we can put the two of them together to get this term here that we want, which is really a surrogate for our A matrix, by just taking those two parts. And so in other words, if we take, try to put them both on the same, if I put them both on the same thing, it gets too small, I think. So in other words, we want dr dx, which is dr dx, which is this term here. And we want dh dr, which is this term here, which is really yeah, this here, multiplied by h. And so it's just those two parts. So this is part Roman 2, and this part is Roman 1. And if I make them big again so you can actually see them perhaps, then what do we have? We have a shape function matrix B prime, which we know. It's just has certain values to it. We have a matrix which includes x1 and x2, the nodes. And we have heads which are here, which are outside here. If we know that the A matrix by definition links the gradients, links the nodal values of heads to the gradients of heads through the A matrix. These gradients are in the global coordinate system, not the local coordinate system. This is the global coordinate system, which is the left-hand side here. These are the nodal values of heads, which are these here. And so by definition, everything else between those is just the shape function. And so we can calculate exactly what those terms would be because we know what they are. If we substitute the values in for this, what do we end up with? B prime is just a half 1 over 2 times this. So this term and this term here are B prime. The product of B prime x is this term here. So B prime x is going to be, if you want to write this out, it's just going to be, so B prime x minus 1 is going to be equal to what? A half times minus 1, 1? Yeah. Multiplied by x1, x2, brackets, minus 1. And so if you write that out in longhand, which I'm sure you can, it's just going to be equal to a half minus 1 times x1 plus a half x2. So it's just actually equal to x2 minus x1. And it's 1 over, which is equal to 2 over x2 minus x1, which is equal to, which is this, which is also equal to what? In this particular case, it's equal to 2 over L. x2 minus x1 is just the length of the element, per se. And so, really, in this particular case, it turns out to be that this value, which is equal to dx over d, no, sorry, the other way around, right? It's going to be equal to dr over dx, which is equal to 2 over L. Works out to be that in this particular case, for certain conditions we have, but the bottom line is that this is just a scalar value. So this term here, that I'll outline in blue, is actually a scalar value, just because it's a product of two matrices, 1 over. And this remains being a matrix. So item number 2, Roman 2, is a scalar value. And if we put this together, then we have those individual components. So we have a value for the A matrix, which is just this. So 2 over 2 drops out. This just becomes minus 1 plus 1 divided by L, right? Because this is just L on the bottom. So we have this relationship here, which was one of our two matrices we wanted. If we go back to this. So we said that we can get this by doing all the manipulations we've done so far. And then if we do that, then this term, which is just this ratio of lengths in x and r, we have that drops out because we've used it already in this other part, and it's just equal to this term here, which is exactly the same term that we calculated here, right? Without the inverse. It's just b prime x. So it's the opposite of that. It's L over 2 by definition. And so what we have is all the individual components to be able to put together the final conductance matrix. And we can imagine what that will look like. So we know that this term here is this. We know that this term here is just the transpose of that, and so we can start putting it together. So this here is A transpose. This here is A. This here is the D matrix. And this here is our determinant, the Jacobian, which is the same as being dx over dr, right? Just the mapping of the lengths. And so we have a single scalar value for this. This is a matrix, this is a matrix, this is a matrix of 1 by 1. If we multiply them all out, we get this. If we want to do the integrations of this, we just have to take one term, and we take that as a k over 2l times the integral 1 dr between -1 and +1. This ends up being r, right? Which is a k over 2l multiplied by r, evaluated between -1 and +1. If you do these substitutions, you get 2 in here, and it cancels out this. I guess that's what this is here. And if you have 2 and 2, then the equation you end up with, perhaps not so surprising, although we've done it a very different way, is that we end up with exactly the same expressions as we had before to represent our conductance matrix. And so that's basically isoparametric elements. So the big picture, I think, hopefully you can see it. It's always good to look at these things with broad brushes. The big picture is this, that we want to be able to figure out exactly what the conductance matrix is. We have a complicated geometry, not so complicated in our case, it's the same element. And we have more than a single node, say, per element. And we want to be able to map it using some other method. And so the method we use is to map it onto this 1 by 1 square in 2 dimensions, or in our particular one-dimensional case, it was just a linear element which was +1, -1, and 0 in the middle that had nodes at each end. And to do that, we have to figure out exactly how we figure out exactly what the magnitude of the A matrix is and what this stretching or compressing component is, which is this matrix. And if we do that, then if you distill down what the principal components are, is that in defining this behavior, we need to be able to do this mapping. And the mapping is that we just use some shape functions which we guess at, serendipity shape functions, which allow us to map the nodal values of heads onto the head at a particular location, and the nodal values of coordinates onto the coordinate value at a particular location in the element. And then if we do that, then the derivatives that are involved in here we can get directly by just differentiating the shape functions. And if we differentiate the shape functions and use them appropriately, then we're able to get the correct element structure, which in our particular case ends up being exactly the same. But it's not completely futile. Of course, it may seem futile in that we've spent an hour and a quarter trying to derive this and then ending up with exactly the same relationship that we had before. But what we could do, and I guess that we'll probably leave this for next time, what if we had an element that kind of mirrors the elements that we talked about already? And the elements we talked about already was an element that looked like maybe this. So in 2 dimensions, the element looked like this. But instead of just having nodes only at the vertices, it had some mid-side nodes and also in one case had some central nodes, with the whole idea of being able to have a larger density of nodes to be able to pick up these high gradients of head. So the analog for our particular case would be that we have an element that would, for instance, have a central node in it. And if that was the case, then in this particular case, we could allow for the fact that as we go from location, if this is the x direction, and this, say, was pressure or head, then, for instance, in our particular case, we could represent something that allowed us to map a head that went from this particular value here as you go across here. So if we only had a linear shape function, then by definition the value of this mid-side node could only ever be equal to the average of these two end node magnitudes. And so if we wanted to represent the fact that there really was a distribution of heads as you go from one location to another, then the only way for us to be able to do that is to be able to put a mid-side node in which case, instead of the equation that allowed us to represent this was previously h is equal to ax, right? And now, in this particular case, it would be a0 plus this plus a1x plus a2x squared. And so this term here is exactly what allows us to get this curvature on this. And so what we could do is we could use all the tenets that we've previously talked about. We could define shape functions that allow us to map the head at any particular location as a function of a shape function multiplied by the nodal values of heads, where now the shape function, instead of being only linear, which we have done, now includes a term that is this, and that then allows us to be able to accommodate this. And it turns out that the recipe, if you like, for developing these shape functions, as we'll see next time, the recipe is only that it has to satisfy the same requirement we talked about before. We said it in passing, but the requirement was that the shape functions have to equal 1 at the point where we apply them, and 0 at every other node. And if we do that, we satisfy the conditions for the system. And I'll leave it there because I see we're going too late. So next time what we'll do is we will talk about why we would do this, not for this very simple system, but for a real system. And the real system is two things. One is we want to use more complicated shape functions, as we've just alluded to. The second is that when we do our integration, we don't just use analytical integration, but we use numerical integration. And so both of those conditions are the kind of industry standards that COMSOL uses. And so that's our reason for exploring it.